Let's talk the tangential and normal components of acceleration. We want to analyze acceleration. And if you look at two vector components of acceleration, the tangential component of acceleration, which involves capital T, the unit tangent vector, and the normal component of acceleration, which involves capital N, the principal unit normal vector, you can get some facts about acceleration that could be useful in analyzing motion. So that's what we're going to do. So this is all in relation to some position function, okay? R of t is the underlying position function, position vector valued function, right? So let's let t, capital T there, v and a all be functions of t. In other words, I'm going to leave off the function notation, the of t part, the parentheses t part, but don't forget that they're all functions of t. Okay, so from what we just got done talking about above, t is v divided by its magnitude, right? So I'm going to rearrange this, and I'm going to derive an interpretation of the acceleration vector for us in terms of t and n. So from this result, would you agree that v would equal the magnitude of v times t? What did I do to get that? Just multiplied both sides of that statement by the magnitude of v and turned it around, right? Now remember, everything's a function of t here. V, the velocity vector, is a function of t. The magnitude of the velocity vector is a function of t, a scalar function. And t, uppercase t, is a function of lowercase t. So we've got a scalar function on the right times a vector function. We can use the product rule once again to find the derivative, which would give us the acceleration vector, right? So working downwards, acceleration, this would be a of t. I'm going to use Leibniz notation for this to start off with. I'm going to take the derivative of the first. So the first function is going to be magnitude v. The second function is going to be t. I'm going to use Leibniz notation here and take d dt of the magnitude of v. That's the derivative of the first. We've got a product here, right? A scalar times a vector. That's the derivative of the first, and then we add that to times the second, excuse me, and then we add that to the first, which is magnitude v, times the derivative of the second. I'm going to mix my notation here. Shame on me. I'm going to call it t prime. Okay? I know. Shame on me. So disappointed in me, I know. Okay, does everybody agree with that? That is the product rule for a scalar function times a vector function. Everybody okay with that? No. But do you understand it? Okay. So this guy right here, this scalar, it's going to be a scalar right here. Let me use purple. This guy right here is a scalar, and we're going to end up calling it a sub t. This guy right here, remember what I'm trying to do. I'm trying to write a in terms of t. Oh, I got that in the first term. And n. I want to get n in the second term. So, well, what is n again? I'm going to make some room here. N is t prime divided by the magnitude of t prime, right? Principal unit normal vector. So anytime you want a particular expression in math, well, not anytime, but oftentimes, you just put it there. But if I divide, really it's multiplication by 1 over magnitude t prime. If I divide t prime divided, if I take that and divide it by its magnitude, that is n, right? I've changed the value though, so how do I compensate? So I better multiply on top by magnitude of t prime, right? Okay. So I'm trying to fit it in right there. So let me move this guy over just a little bit more. Okay. So good news. This guy is n. Right now you're thinking, why the heck is he doing this? And that's okay. Just make sure you follow the steps symbolically, and then I'll explain everything. So that guy's n, right? The stuff in front of t and n have interpretations that are useful. So first of all, this d dt of the magnitude of v, well, what's another way to think of the magnitude of v? ds dt, right? So this guy here is ds dt. We're taking d dt of ds dt. That's a second derivative, okay? So this thing that I'm calling a sub t for some mysterious reason at this point is, okay, how do you write the second derivative in Leibniz notation? So d dt of ds dt, it looks like multiplication, right? So d2s dt squared. So this guy, d dt of the magnitude of v, becomes the second derivative of s with respect to t because magnitude of v is ds dt. I know, it's going to be information overload. But does that make sense at this point? Don't try to remember everything at once. You'll drive yourself crazy. Just little piece by piece. So that's times t, right? Okay, so that little piece is like the acceleration that you found in Calculus 1. It's straight line acceleration. What does the unit tangent vector give us? In the microscopic, it's telling us about the motion straight ahead or along the curve, right? And so this is the rate of change of the rate of change well, let me call it the rate of change of ds dt. It's the rate of change of the speed. More on that in a minute. Now, over here, I've got my n, so I'm gonna keep that n, that guy in purple. I'm gonna keep that n, and then I wanna come up with an interpretation for this guy. Well, it's gonna be convenient. I drew that purple cloud a little too quickly there. It's gonna be convenient to get k in there somewhere, curvature. And what was a formula for curvature that has a magnitude of t prime in it? This one, right? That one right there. Okay. So magnitude t prime divided by magnitude r prime. Okay. So if I want to throw curvature in here, what do I need to divide this thing by? The magnitude of, well, okay, wait. It's the magnitude of r prime at t, but isn't that v? Inside the magnitude bars, isn't that v of t? Okay, so I'm going to write it as the magnitude of v. It's of t, little t, but we're not going to put that in there. Wait a minute, what do I have to do to compensate? I've got to multiply on top by that, but that just squares that magnitude of v, right? Okay, so what do I have in front then? In front of the n, don't forget I have a plus here. Now, magnitude of v is ds dt, but this magnitude of v squared then would be ds dt, the whole thing squared. It's not a second derivative. It's the square of the first derivative. And then this guy here, magnitude t prime divided by magnitude v is k. Okay, whew, that's it. That's the final form we're going to use here. Okay, does everybody, you may not be comfortable with that, but does it make sense symbolically, algebraically so far? That's what I'm after. Okay. So let me point out once again, this guy in front of the t, we're calling a sub t. It's a scalar, right? And that's going to be the scalar component of the tangential scalar component of acceleration. So a sub t can be thought of as d dt of magnitude of v, but it's equivalent to the second derivative of s, arc length with respect to t. And then this guy in front of the n, the ds dt squared times k, that guy is a scalar, and we're calling it a sub n, the normal scalar component of acceleration. Okay? So we'll take a look at what this means in a second, but did the math make sense? I wanted to go over that in a very careful way because if you're not careful, it doesn't make sense.